All right, let's get right into it. Today we're going to talk about one of the most clever and, honestly, elegant shortcuts in all of chemistry. It's called Hammond's Postulate, and it's this amazing tool that lets us understand the single most important and completely invisible moment of a chemical reaction.
But that kind of begs the question, right? How do you study a moment that's over before you can even measure it? How do you describe something you literally cannot see? This was a massive problem for chemists for decades, and the solution they came up with is just remarkably smart.
So, to get our heads around this, let's use an analogy. Imagine any chemical reaction as a journey over an energy mountain. You start in the reactant valley, and to get to the product valley on the other side, you got to climb over this peak. And that peak, that's the highest point of the climb. It's the most critical part of the entire trip.
And that brings us right to the heart of the problem, what I'm calling the reaction's invisible peak.
This peak has a formal name, of course. It's the transition state. It's the highest energy arrangement of atoms anywhere on that path from start to finish. And just look at that lifespan, 10 to the minus 13 seconds. That is a fraction of a trillionth of a second. It's basically a molecular ghost. It's there and gone so fast there's no way to isolate it or study it directly.
So you can imagine the headache for chemists back in the 1950s. They knew this transition state was the key. It controlled how fast reactions go. Because, the height of the mountain determines how hard the climb is. But they had absolutely no way to see what was actually happening at the summit.
And this is where the genius of a chemist named George Hammond comes in. He came up with a powerful shortcut to solve this exact problem. So in 1955, Hammond published this postulate. Now, it sounds a little academic, I know, but the idea at its heart is actually incredibly simple. What he's saying is, if two spots on our mountain climb are close together in altitude, or energy, then they must also look very similar in their structure.
And that is the shortcut. That's the whole thing. To figure out what our invisible ghost at the peak looks like, all we have to do is ask one simple question. Is the peak's energy closer to where we started, the reactants, or where we're going, the products? The structure of that peak will just look like whichever one it's closer to. It's such an elegant solution to this huge problem.
Okay, so let's see how this actually plays out. There are really two main types of journeys you can take over this mountain, and they lead to what we call early versus late transition states.
So we've got two main scenarios. First, you have an exothermic reaction. That's an overall downhill trip, where the products are more stable. They're lower in energy. In that case, the peak is going to be closer in energy to the reactants. We call that an early transition state. The exact opposite is true for an endothermic or uphill reaction, which gives us a late transition state that looks a lot more like the products.
Let's look at this visually. Here's that first case, the exothermic or downhill reaction. You can see it clear as day. The peak of that energy curve is much closer in height to the starting point. So Hammond's postulate tells us the structure at that peak must look a whole lot like the reactant structure. It's an early summit.
And now, here's the flip side, an uphill endothermic climb. The product is way up there, much higher in energy. And that means the peak is now energetically much closer to the product. So, what does the transition state look like? You guessed it, it looks a lot more like the final product. We call this a late summit.
Okay, so we can predict the structure of the peak. Big deal, right? Well, it is a huge deal. This is the crucial part, because it helps us understand this really deep connection between stability and speed.
Knowing what the transition state resembles is one thing, but how does that actually tell us how fast the reaction will be? How does it help us predict the speed of the climb?
Well, to answer that, let's dive into a textbook example that every single organic chemistry student has to learn, the formation of carbocations. Just think of these as really high-energy, unstable intermediates. They're like temporary pit stops partway through a reaction.
Now, here's the key. Not all carbocations are created equal. As you can see here, a tertiary one, that's the one with 3 carbon groups attached, is the most stable. A primary one is the least stable by a long shot. And this difference in stability, it's the key to everything.
And here is where it all clicks into place. The path to form the more stable tertiary carbocation has a lower energy peak. Hammond's postulate tells us why. Because that more stable intermediate is closer in energy to the starting material, it actually pulls the transition state, the peak leading to it, down in energy. And a lower peak means a smaller mountain to climb, which means a faster reaction. So, here's the bottom line, the crucial point. More stable things form faster. By making the intermediate more stable, you automatically make the transition state peak leading to it more stable too. You lower the energy mountain. In chemistry, stability directly translates to speed.
But reality is rarely a single, simple path up a mountain. What happens when the landscape gets a lot more complex?
Our energy mountain analogy has been pretty simple so far, right? Just a two-dimensional line. But real reactions are multidimensional. What if there are multiple competing paths, different valleys and ridges, all on the way to the top?
But here's the truly amazing part. Even in this super confusing, complex landscape, Hammond's postulate is still our compass. That same basic intuition that the path will always be drawn toward regions of lower energy and greater stability is what allows chemists to read these crazy maps and predict which of the many possible trails a reaction will actually take.
And the stakes for getting it right are just incredibly high. Just look at this quote. A tiny, tiny difference in the height of that energy barrier, just 1 kilocalorie per mole, which is an almost negligible amount of energy, is enough to completely flip the outcome of a reaction from, say, 70% of one product to just 30%.
And that, right there, is the ultimate takeaway. Hammond's postulate isn't just a rule for chemists. It's a really profound principle. Tiny, almost invisible differences in stability at the start of a process can end up dictating the entire path and have a massive impact on the final outcome. It really makes you wonder, doesn't it? What other complex systems in our world might be following this same simple, powerful rule?